Okay, so problem number 1 has me going over a hill, a bump in a hill, and we can approximate the hill as a circle of radius 50 meters. And here's my body. Let's say we're just looking at my body in the car, and it's moving alongward at this direction. Let's not put that arrow in there because I'm going to start thinking it's a force. But really, all I know is that I have a velocity equal 20 meters per second, and it's in this direction. Okay, so I've got that. Come on. And my mass is equal to 70 kg. Okay, and so the question is, what is the scale reading under me? And we know what scales read is they read normal force. They presume you're in a gravitational acceleration and they read normal force. And so first thing I say is, yikes, this is very complicated. I sit back, what do I know for sure? I know for sure that the vector sum of the forces is equal to mass times acceleration. Okay, and I wonder if I'm accelerating. This is a constant speed, but I'm going in a circle of radius r, so I recognize that there's some centripetal acceleration, which is equal to v squared divided by r, right? And here I could write, I know what the acceleration is, because this thing would keep going straight if there were nothing accelerating it. Force of gravity is going to help accelerate it downward, and it's accelerating into the circle in this direction. So we know the vector sum of the forces, the resultant force, must also be in this direction. We could put in numbers and find out what that acceleration is. That's 20 meters per second. Don't forget to square it over 50 meters. It's 400 meters squared per second squared over 50 meters. I look at units first because they're very important to me. We lose one of the meters and I have meters per second squared. I'm delighted because that's acceleration, should be meters per second squared. And then we've got 5 into 40, that's 8 meters per second squared. So is this realistic? We look at that and, oh, that's almost a gravity. I'm accelerating downward here, almost as if I was falling, free fall. So yeah, that's very possible. And we look at, what are the forces acting on me? Well, I know I've got gravity, and that is, force of gravity is mg. And if that was the only force acting on me, I would be accelerating downward at 10 meters per second squared. But it's not the only force. The scale is pushing up on me. A normal force is pushing upward. And so right now we can look at this and see the normal force. If it were 0, I'd be accelerating downward at 10, but I'm accelerating downward at 8. So it's not 0, but it's much less than gravity. So I could just go into this equation now and say, look, the normal force pushing up, the sum of the forces are normal force, plus the force of gravity, is equal to mass times acceleration. Right now I've completely neglected sign, so let's pick a positive direction. I'm going to pick downward as a positive direction because most of the stuff is going on downward, and that means the only one that is negative is the normal force. Okay, the normal force is the one we want, so we solve for it, and we have the normal force is equal to then force of gravity minus mass times acceleration. And this makes sense because if this were 0, these two would be equal. So the normal force is going to be less and less because the acceleration is downward. It doesn't have to compensate for as much of gravity. Or if we look at it from vectors, we could say, look, here's the force of gravity. If that's the only force, that's the total force acting on you, you accelerate downward. If you have a normal force like this, that means the total force is this much, right? If you were accelerating upward, so for instance, if if this was, if you were in a circle like this, accelerating upward, you would know that the total force would have to be upward, and so your normal force would be bigger, right? Giving you an upward resultant force. Okay. So in any case, let's take a look at this now. So the normal force is then equal to the force of gravity is mg minus ma is equal to 70 kg times 10 meters per second squared minus that's 70 kg, let's watch me run out of room, times 8 meters per second squared. And so finish the problem. What do we have? We have 700 newtons is a force of gravity pulling down on me, and 560 newtons is what's used up accelerating me into that circle. So what I have for my normal force is 140 newtons. So 700 newtons pulling down, 140 newtons is what the normal force is, very little, so you feel somewhat weightless or somewhat normal forceless. And what's left over is 560 newtons accelerating you into the circle. So what does the scale read? Well, if it were in force, it would be 140 newtons, but the scale expects that you're in gravitational acceleration of about 10 meters per second squared, so it would just tell you, it would think 14 kg is what this it would read. In any case, the scale would experience 140 newtons, but it would read in mass, because usually they do, of 14 kilograms.